Boom. All right, gentlemen, welcome to chapter 5. Yeah, we're making progress. We are left with just one chapter to finish. You have just about 6 chapters in this amazing Maths 1 to 5. So, chapter 5, chapter 5, chapter 5. The title of chapter 5 is Motion of a Particle. Motion of a particle. And of course, the motion of the particle we're going to be discussing here is going to be in 2 dimensions when an object is dropped from a height to the floor, and then when an object is thrown vertically upward. What motion or what are the parameters that will associate this particular object either going up or going down with respect to distance, displacement, and relationship between distance and displacement. That is exactly what we are going to be discussing as far as this amazing chapter is concerned. So let's go into the chapter properly. Motion of a particle. When a given particle is in motion, the resistance per unit mass of that particle is directly proportional to its limiting velocity. Take note. Resistance per unit mass of a particle in motion is directly proportional to its limiting velocity. Resistance per unit mass directly proportional to limiting velocity. But opposite to what? Opposite to what we refer to as force. Yes, the resistance per unit mass is actually opposite to the force. In fact, the resistance is opposite to the force, not the resistance per unit mass. The resistance itself is opposite to force, isn't it? Good. So the equation becomes R over M, which is the resistance per unit mass, directly proportional to V. If you work at that very well, R becomes MKV, right? Good. Now, and also F is equal to minus R. That is the opposition we are talking about. So if you work into this expression that F is equal to minus R, you are going to end up having F there is mass times dv dx, right? F is mass times acceleration. Acceleration is dv dt. Good. So m dv dt is equal to minus mkv. And then, of course, if you cancel out the m and bring the value of kv on the same direction with dv dt, you equate it to 0 and you have a linear dE, right? A linear dE because the value of q of x or q of t is equal to 0, isn't it? Good. So this is linear. And because it is linear, you can either solve it by variable separable or probably integrating factor if you like. But I think variable separable is the best way to solve linear dE, right? So that takes us to the 2 basic tranche of this topic, which are the upward motion and the downward motion. We start with the downward motion because the body is moving in the direction of gravity, so your mg is positive. If it is moving upward, it is against gravity, so your mg is negative. So F here becomes plus mg minus r. F becomes plus mg minus r for an object being thrown from a top to a bottom. That means it is going downward towards gravity. So from there you can derive the equation. F, of course, is m dv dt being equals to plus mg minus r there is mkv, isn't it? So cancel out the mass and then you get an equation. Of course, the equation you're going to have at the end of the day becomes dv dt plus kv equals to g. And that gives you, let me use the word, that gives you a derivative where q of t is not equal to 0. And of course, when q of t is not equal to 0, you refer to it as a non-homogeneous, right? A non-homogeneous linear dE. So not really non-homogeneous. Yeah, it's non-homogeneous linear dE. And you can actually solve this by variable separable. So all you need to do is to solve it by variable separable so as to get the value of the velocity of that particle. Because the potential question that can actually come from this downward motion is that what is the velocity of such particle? Or what is the distance covered by such particle? Or what is the relationship between the distance and the velocity covered by such particle? Those are the 3 potential questions you're going to see. So we start with the velocity covered. So that dv dt plus kv equals g. Solve it by variable separable. You're going to get a solution in terms of a constant c, right? Good. Now, that constant c, you have to find its value. And for you to find the value of c, you have to assume final velocity to be 0. And then, of course, at a time t equal to 0. Why do you make such assumption? Of course, the body is being dropped from a given height and is hitting the ground. So at a particular position up there, the final velocity is 0, and then the time is also 0. That will help you get the value of c. And by the time you do that, your value of c is going to surface. And once you get your value of c, you substitute it back, and you have an equation for the velocity, which is going to be g all over k in bracket 1 minus e raised to power minus kt. That g all over k represents the limiting velocity. Limiting velocity. Very, very important. Limiting velocity. Take note of that. Limiting velocity is simply gravity divided by the constant k, right? So having gotten the velocity, the next thing you'll be asked to calculate is the distance. And how do you get distance from velocity? Integration, isn't it? Good. You have to integrate because you're moving backward from velocity to distance. So you integrate. And for you to integrate properly, you have to change that v in that formula you got for velocity to be equal to g all over k1 minus e raised to power minus kt in close bracket. That v becomes dx dt. Cross multiply, integrate both sides. And once you integrate both sides, you will get your answer in terms of another constant, maybe a. So you have to look for the value of that a, assuming x to be 0 and time t to be 0. You get the value of a, and your a there becomes minus g all over k, as the case may be. So by the time you have that, you substitute back in your equation, and you're going to have the distance proper, which is going to be gt all over k plus g all over k square in bracket e raised to power minus kt minus 1. Then close the bracket. That becomes the distance covered, right? Good. Now, if you want to calculate the relationship between the velocity and the distance covered, then that formula I told you in chapter 4 becomes very pertinent about acceleration. Do you remember? Acceleration is the product of velocity and dv with respect to dx. Good. So if you remember that vividly, just fish out your formula again. F is equal to plus mg minus r. Your F there becomes mass times acceleration, which is mass times velocity times dv dx, equal to plus mg minus mkv. And then from there, you can actually derive the equation, which is an equation of a dE, which you're going to get. So that dE you're going to get, you can solve it by variable separable so as to get the relationship between velocity and distance. Now, take note. For you to get the value of the constant there, you will have to solve that at a velocity of 0 while a distance of 0 as well. In fact, for you to get a constant in this chapter, just make the two parameters 0, 0, okay? And that will get your job well done. And then when you do that, the relationship between distance and velocity will be velocity, which is distance, which is x equals v over k plus g over k square, open bracket, ln g all over g minus kv, close the bracket and reclose. So that is exactly what it will give you. So that is how you calculate the velocity, the distance, and the relationship between velocity and distance in particles of motion, right? Now, take note, what we have just done is the downward motion. You got to do the upward motion too. So how do you perform the upward motion? The upward motion is just a difference of minus. Your F becomes minus mg minus r, isn't it? In most cases in exam, they will just stop at F equals minus mg minus r. The highest thing they will do is to substitute F to be equals to m dv dt to be equals to mg minus mkv and stop there. You know, very crazy. But at times they don't even go into the details of asking you for distance, asking you for velocity, and the relationship between velocity and displacement. They may not even go to that extent, but it's good you study it just in case. You never can tell when the demon will wake up. You have to be prepared at all times. So for you to do that, once you substitute your values for F to be m dv dt, your plus minus mg minus mkv, you're going to have an expression which is also a dE. That dE you're going to have at the end of the day, you apply variable separable method so that you can get the value of v, which is the velocity, the constant that you're going to get there at the end of the day. Substitute it at v equals 0, t equals 0, so that you get the value of the constant. And when you do that, your velocity becomes g all over k bracket 1 minus e raised to power minus kt plus c, as the case may be. Of course, you will have found the value of c, as the case may be. So now that you have V, for you to get the distance, the same parameters, change V to dV dt to dx dt, cross multiply, integrate both sides, and then get your value of x as g over k in bracket 1 plus e raised to the power minus kt all over k, close the bracket. Then for you to get the relationship between, these values I'm giving you are actually values of the downward motion. For the upward motion, the difference is just minus, okay? So V becomes minus G, that's for velocity now, minus G all over K plus, in bracket V naught plus G all over K, all in bracket e raised to the power minus KT, right? Good. So here, as for the distance, you're going to have V all over K plus G all over K square lane, open bracket, G all over G plus KV, close the bracket. Then for you to get the relationship between both of them, which is actually X or H as the case may be, minus V all over K plus G all over K squared lane KV plus G all over G, close the bracket. So basically that is that for this chapter. Ladies and gentlemen, Mr. Juleben, we are done with this amazing chapter 5. And we move into the last chapter, and that is a great chapter we call Motion in an Inclined Plane, Stroke Work Energy and Power. Boom.